So I hope you can see it in full screen mode.
Yes, we see it. We see it.
Okay,
Thanks.
perfect. Okay, morning everyone. My name is Aamir Mahmood and I'm Associate Professor at Michigan University. In this talk, I will be talking about this remote teleoperation use case. Teleoperation, I mean here the ability to operate some heavy machines from a remote location. And when we talk about the remote areas, because if we want to do the teleoperation, it's a demanding connectivity use case for 5G and 6G, and then there is a lack of infrastructure on the remote areas on the northern side of Sweden, Finland, and all these areas, Nordic countries. So then I will be sharing our experiences based on the two Vinnova funded projects that we had together with some industrial partners. So what are the connectivity needs, and then what kind of infrastructure we need to support this kind of use case, especially in the you can guess from the picture, is more about the timber handling, because these northern areas, it's the timber heavy industry. So it's related to both the management of the forest supply chain. So here, quickly about the agenda, I will quickly talk about the different use cases of teleoperation and then focus on the forest industry vertical. Then I will just give some the needs and challenges that we faced while tackling this forest supply chain management. The project name was to remote timber. And then the continuation of that was going more towards building a robust wireless infrastructure for that use case based on what we learned from the first project. And then I will just give some opinion about where we see the future of teleoperation and what we learned from these projects and what we have for 6C going forward with this use case. So teleoperation, as I mentioned, the ability to control the machines from a remote location. So the areas are diverse. It's more about port automation. It could be used in construction, automation, mining industry, and as I mentioned about the forest industry. So the needs could be different. It could be about handling the dynamic loads at port automation. In the construction automation, it could be the dangerous situations where we don't want the operators to operate at that location. It could be any other hazardous conditions. And then it could be related to basically, if we go for mining and automation, it could be the ore extraction or it's the transportation. And then the forest industry, it covers a wide area. So if I stole this slide because SCA was the project partner. And when we're talking about, okay, why even this Starlink, for example, why they don't have the connectivity in the northern areas. So probably it's what we see that probably we need to advocate the needs, connectivity needs in these areas. So here it shows on the left side the forest that is owned by SCA. It's from if I take the pointer. So here I'm putting this Sundsvall as a reference because they have own the forest in the northern part of Sweden. And on the right side, it's the different operations that are happening because SCA owns the forest and then they maintain. It's not only about cutting the wood, but also maintaining those ones, preparation of the soil and planting new trees. So all these activities are happening in the northern areas. So in this case, if we where the wood is felling, I mean, they are cutting the wood and then it's transported to some terminal, some intermediate points where the wood is stored. So even where the wood is cut, like usually they have one harvesting machine, one forwarding machine that is loading the raw wood to the trucks, and then it's transported to some intermediate location. They call it timber terminal. So that's where it is stored. So here they have many, around 200 sites where these actions are happening continuously. So far, they are saying like, okay, it's operated manually, but in future, it's just they are reporting, okay, what is the logging operation that is happening at this moment at this site, and they get the next task. Okay, now they should move to this site. So in that case, they are talking about, okay, they need the coverage needs, but in future they want to automate that operation. So the machines, the ability to operate the machines from a remote location, because the manning of these sites is always difficult and challenging. So here, in this the first project that we had, the remote timber, we were focusing mainly on the wood is coming from the forest, transported. But when it comes to this timber terminal, they have 15 sites in this northern part. But in general, in Sweden, there are almost more than 100 sites where there are timber terminals where the wood is coming and stored, and before it's forwarded to the industry or the factories. So in this case, the objective was when the wood is coming here, this heavy wheel loaders that are like 40-ton wheel loaders, the task was to operate these wheel loaders from a remote location. So it's the automation of this workflow for loading and unloading, and we did this use case. The If we have one operator sitting at a remote location, it has the ability to operate four timber terminals. So uh, it covers this manning needs of these terminals. Mostly they are in a remote location, so manning of these timber terminals is a bit challenging. But what we face is mostly these are in the remote locations, and if we talk about the teleoperation use case, it's a challenging use case in terms of connectivity needs. So it has, because to operate this machine, you need to have multiple views. This machine, it's not only the driving this machine, rather it has to do the intricate operations, the handling of the wood, loading and unloading, and storing that wood to the right place. So it's an uplink heavy use case in terms of the video transmission that this machine has to send to the remote location to the operator so that he can operate this machine. So in that case, first of all, lack of connectivity infrastructure, and then fulfilling this demanding connectivity needs of this use case is challenging. So this is how a typical timber terminal looks like. It spans over around 3 to 4 kilometers, and the wood layout is not fixed. It keeps dynamically changing depending on how the wood is coming and how it is moving out of this timber terminal. So it's this site is close to Sundsvall. It's called Toshpara. So we did some drive tests. The nearest base station here was about 3.5 kilometers, and we were looking at what is the throughput that we could get at this location at different places, and then what is the latency. So here, what we observed, based on the basic test, the data rate we could achieve here was 1 to 10 megabits per second at max. As compared to that, if we look at the round trip time using simple ping commands, so it was reasonable within the range. I will express what were those connectivity needs coming from Volvo to operate these machines in a safe manner. So the ping was around 60 to 80 milliseconds, but 60 to 80 milliseconds. So that was fine, but ping is a very simple way to test the round trip time, because it's not testing how the network will behave under different load conditions. So it's not generating the realistic traffic in that case. So in that case, uh, we went towards selecting a certain section within this timber terminal, installing a dedicated base station on that one, and just to provide the coverage in this area. So this was our test area where this vehicle heavy loader was operating. And then the operator was at the same location, but the traffic was routed through Stockholm to I mean, this is going to the core is in the Stockholm, so traffic was routed to Stockholm and then coming back to this operator. Operator was located at this, so it was maintaining two sectors, one towards the vehicle, one towards the operator. And this is how the how, if we look at, this is where the vehicle is operating, and the timber height could reach up to 10 to 15 meters in that case. And for the operator, this was the analysis that was done. Okay, now to have this the operator to operate in this kind of environment, how many views he needs to operate this machine in a comfortable manner. So there were 11 cameras installed on the vehicle. But there was a proprietary tool that is stitching all these streams together, transmitting, and then uh, received by the operator. So in this case, the requirements that was set was to support all these views, there was a requirement on 50 megabits per second in uplink direction with the latency of 200 milliseconds to operate this machine safely. So whenever the latency threshold was exceeded, so in that case, the watchdog timer on the vehicle triggers and it goes into the safety. It just shuts it down, so it's remains static. So in that case, the operator has to go to the machine and then it has to reset. So during these tests, the tests were conducted over a week. So every day, 2, 3 times, it was happening that the machine was shutting down because it didn't meet the connectivity needs. So here it's a one quick video. I hope you can see just the wheel loader without operator on itself. So this is how it was handling the wood operations. So in this case, I mean, the drivers, they needed certain training before because they lack certain haptic feedback that was not provided. They because a lot of things they judge based on the how the vehicle is behaving when they lift the load or no sound, nothing. So in that case, they needed some training, but they wish they could have the vibrations that they feel when they are really operating that machine. But after certain training, they were able to handle these operations. The other one was about this, the difficult task was this depth estimation when you are loading or unloading. So these certain boundaries, it's hard to guess. It's difficult, the depth estimation. So that was the good side. Okay, now we have the successful demo, but then if we look at the ugly side, so if I look at some results, in addition to that, I mean, they were operating the machine, we were conducting some measurements. So in that case, what we see was, okay, if we look at these bounds of 200 millisecond, if it is a line of sight condition, I showed you that the area in which the vehicle was operating. So if it, as long as that vehicle is in the line of sight area, it satisfies the connectivity needs. But as soon as you go out of that connectivity zone, you start violating those requirements quite quickly. So just imagine then we want to provide the connectivity needs in the whole timber terminal. So then what kind of infrastructure we need? And the same was for the throughput requirements in the non-line of sight conditions. It was not satisfying the requirement of 50 megabits per second. So if we look at how the network was configured, it was a lot of overprovisioning of the radio resources. 1800 megahertz band was allocated 1900 megahertz band as well as 3.5 gigahertz with TDD with certain uplink downlink distribution of resources. So in that case, with this overprovisioning of resources, how feasible is that from the or the one who owns this from the operator perspective, or the one that is the end user is the SCA, for example, in this case. So what are their how to allocate these resources in an efficient way? That's still challenging. And then as we move out of this coverage zone, the performance degrades quickly. Then if we look at the timber terminal, it's more a stationary the timber terminal, I mean, the terminal is stationary, but if we look at the wood layout, it's always dynamic. So in that case, it needs more flexible network infrastructure that could handle this connectivity needs. And then we are just operating one machine and it's uplink heavy use case. So how to satisfy those connectivity needs? So based on this, what we learned, then we move forward to the next project phase where we envision that, okay, we need more we need to play more with the RAN architecture, how the RAN architecture is defined to provide coverage in this specific timber terminal. And then also the network slicing. I mean, these new features are coming from 5G, 6G, but they were not exploited. How to handle the let's say the video traffic, the control traffic, because the control is running in parallel with the video feedback that is going to the operator. And then how the videos itself, they are handled on the vehicle side. So operator is given all that information, all this raw information is transferred to the operator, and he is acting based on that. And what if we use more intelligent methods on the MEC level to reduce the uplink demand, basically? And then the other direction that we envisioned was more drone-mounted 5G base station to extend the coverage to provide the connectivity needs on the timber terminal. And then other KPIs that we set. Then to provide this different coverage options, that's where we took. There were two options. Either we have a local core and a flying base station on a drone, and then it provides the connectivity. I mean, fulfills these coverage holes in that timber terminal. And the other option was that was coming from SCA. At some places, they do this drone, lift up the drone just to so that the others the tower comes in visible range, so that at least we have that typical UE. It's more like a UE, and it has the coverage to the connectivity to the base station. And then it could provide either this access could be 5G or it could be even Wi-Fi in that case. But the one that we demonstrated was it was in Västerås. So in that case, we had the local core. It was not 5G core, it was 4G core that is provided by Ericsson, that is tested in a lot of different situations. So that's why they didn't went towards 5G setup, but it was a local core, and then we had the drone mounted base station. So in that case, I mean, I will show the demo later, but the forwarding machine that was used to test this the connectivity. But in parallel, we did some additional tests. Instead of ping, we use this TWAMP. It's more like a two-way active measurement protocol that allows you to generate different kind of traffic patterns as well, different payloads, and so that is more appropriate as compared to just using pings to measure the network performance. So in that case, we were testing and this drone base station, the local core was connected to Starlink, and then we had the server, the the receiver side was in the AWS server. So in that case, what we observed, surprisingly, the Starlink was providing quite good enough latency. It was like, if we look at the minimum is around 55 millisecond, and the maximum latency that we could see is around 160 milliseconds. So that was satisfying the connectivity needs. And the same, if we look at this forwarding machine, this machine was operated from remote Uppsala. I forgot the distance between Västerås and Uppsala, but it's 80, 90 kilometers or something. So then we had the drone flying above with the base station. This was around 30, 40 meters, and it was providing the coverage. The coverage was around 3 to 4 kilometers. And then this project is still continuing.
Can you start to wrap up? Or?
Yes, yes. So this project is continuing, and then we are looking at the MSC, the role of MSC to reduce the uplink information transfer. We are looking at the super resolution algorithms to reduce the data rates, to compress the videos. This is what we see for the future, as I think Nurul already mentioned about this multi-model data fusion, where instead of giving this raw information, we rather need to go more abstraction of the details provided to the operator to operate in this machine. But the challenging is, I mean, it's not only about the driving itself, but then we need to learn about build this environment model, driving model, as well as the task model. That's the actual loading and unloading of operations. So this is the last slide that I have, the future of teleoperation. So, I mean, is it something that we need to handle something differently in 6C? But we need more holistic approach. But as Nuro also highlighted, we need to bring in the context of the application and of course, the AI/ML to co-design of communication and control for this kind of use case. These are the project partners, and this project also got the Seal of Excellence from Royal Swedish Academy of Engineering Sciences. It was selected as top 100 project with more impact on the more impact on the society, and is more ready for the commercialization phase. Thank you.
Good. Thank you, Aamir. So that was very interesting. I think we learned a lot about this vertical. I was thinking, okay, I will allow one very short question if there is. We have little time, so keep it short.
I'm not sure it's short, but try. So what we observed when we did measurements with the Starlink, that there are connection breaks up to 10 seconds or sometimes even longer. Have you done driving tests to see how these breaks impact to the driving experience?
They were experiencing some jitteriness. Probably we couldn't isolate, okay, those are because of those brakes or something. Is it because of the handover mechanism, or why there are brakes? I didn't know that.
Probably it's related to handovers, at least these long ones. So the next satellite, it's coming a bit late or something. But you do the measurements, and maybe it would be, if you are really doing this, how the driving experience, maybe it would be good to include these brake counts, brake durations counts also to these analysis or measurements.
Okay, thanks.
Good. Excellent. Thank you, Aamir, once again.